So I hope you are able to see the presentation.
Yes, sir.
Okay. So the main thing is that in the case of two-way slabs, you will be having predominant bending along both the directions. So you have to provide reinforcement to restrict this deformation in both these directions. Okay. And to start with, whether we have to just classify and start or adopt a method, whether we should go with the method of one-way slab or two-way slab. For that, we will be using the expression Ly by Lx, and please note Ly will be always the larger dimension. Okay, so sometimes you will be having two along one side, you will be having 2 meters, and other way you will be having 2.2 meters. So 2.2 will be always your Ly. Larger dimension have to be substituted as Ly, and if Ly by Lx is less than 2, that means you have bending predominant in both the direction. We can adopt that method for the design of this type of slabs. And for any sort of interview or something like that, you are asked the same question: how can you classify slabs? You have to clearly mention that the slabs can be classified based on the way in which they are bending, not based on the ratio of Ly by Lx. Okay. Now regarding the design of one-way, regarding the design of two-way slab, that is a mistake. Two-way slabs, we have two separate sections. One is regarding the design of simply supported two-way slabs, and the second one is regarding restrained two-way slabs. So the main difference between these two is, so can someone tell me what is the main difference between these two? So basically, if you are considering the side view of these slabs, say your simply supported slab will be like this. You will be having the support, and the slab will be simply resting on this. This is simple support. Okay. So once you subject the slab to loading, what will happen is that, so you again will have these supports here. This slab will bend like this. This is exaggerated figure. So don't expect that you will be seeing this much gaps in the actual structures and all. Okay. So your slab will be, the ends will be free to get rotated. That is the main thing. If you see the end, it will be free to rotate. Sometimes what we what will be there is like, these slabs will be monolithically cast with this support. So you will be having reinforcement going inside, or some sort of arrangement will be there by which this ends will not have the provision to get freely deflected. Sometimes what will happen is that you will be having a support here, you will be having your slab like this, then you will be having another support here. That means this end is fixed now. It cannot freely rotate. There is a compressive action which will restrict or restrain this end. So this end in this case is considered to be restrained from rotating. So that is another case, case B, and this is our first case. That is the case of a simply supported slab. So we have different procedure to be adopted in both these cases. So first thing that you have to understand is that you have to, in the practical field, you have to check whether the condition will be a simply supported case or it will be a restrained case. Okay, and based on that you have to select your procedure. So we have two methods. One is for simply supported two-way slabs, and another one is for restrained two-way slabs. And the design of two-way slab can be performed based on the procedure given in the Annex D of your IS 46-2000. If you refer your code towards the end, you have different annex from starting from A to I think E or F. Some annexes are there, and in that the Annex D corresponds to the procedure to be adopted when you design your two-way slab. Let's go to that annex and discuss the remaining things. So in the Annex D, we have the provision for design of two-way slabs spanning in two directions. So in that, if you see the first clause, that is D1, it is regarding the restrained slab. So when we have, or when we have to design the restrained slab, we have to adopt the procedure given in D1, and then we have one procedure mentioned in D2 which deals with simply supported slab. So first thing is that based on the condition of the support, we have to select any one of the method from this. Clear? Now we will just go back to the PPT and come back here. So design based on Annex. So first of all, let's see the design of simply supported beam. After that, we will go to restraint slab. So based on the design provisions given in Annex D, first thing is we have to calculate the moment acting about x-axis and y-axis. That is, we have now we are dealing with a slab which will be bending in both the direction, in the x direction as well as in the y direction. So for designing the reinforcement along the x direction as well as y direction, we need some moment. We have to consider some external moment which will be acting, and based on the equation we can calculate the AST corresponding to, or the AST required to calculate, means carry that much moment. So basically first thing is we have to calculate the total moment acting along x direction and total moment acting along the y direction. So for that, this Annex is actually suggesting two equation. In order to calculate the moment along x-axis, we have the equation alpha x into W into Lx square, and similarly to work out the value of moment acting along y-axis, we have the equation alpha y W into again Lx square. It is not Ly square. Please focus here. In both the equation you have Lx square. This is not mistake. It is intentionally given that Lx square. Okay, so if you come back to the code also, you can see here in the case of simply supported slabs, what is given there. When simply supported slabs do not have adequate provision to resist torsion at the corner, that is, it is free to rotate, and to prevent the corner from lifting, the maximum moment per unit width are given by the following equation. Okay, maximum moment per unit width. We know that when we design slab, we will be taking the width as 1 meter. So per width is given by the following equation, and the equations are mx is equal to alpha x into w into lx square, my is equal to alpha y into w into again lx square. Okay, and mx, my, w, lx, ly are same as shown in D1.1. What is D1.1? That is regarding the restraint slab. So here they have given the definitions for alpha x and alpha y. What is alpha x and alpha y? They are the coefficients given in table number 26. Okay, the alpha x and alpha y can be calculated from the table 26. We will look into that later. Then we have W, that is the total design load. That means it should be your factored load based on the dead load. Then you will be having live loads. Then we will be having floor finishes. Then sometimes you will be having other sort of finishings. So all that load should be added up, and that should be factored, and that should be considered as your total design load. Okay, so once that is done, then what is mx and my? Moment on strip of unit. So regarding this, mx and my will be the moment acting along x direction and y direction. Okay, please don't go through this and get confused. We will explain this in detail when you come to restraint slabs. Then Lx and Ly are, you already know, that is length along the length of shorter span is considered as Lx, and length of larger span is considered as Ly. It's always like that. So that is how you will calculate the moment in this case. This is the major difference in the case of two-way slab. Please do understand, in the case of one-way slab, if you remember, we used to calculate the dead load, live load, and other loads that is acting on the slabs, and after that we will be calculating using the equation WL square by 8, or accordingly, whether it is a cantilever slab, you will be calculating the maximum moment accordingly. Okay, but in the case of two-way slab, this is the major difference. The moment should be calculated using the coefficient method, that is using this equation. Mx should be calculated as alpha x into w into Lx square, whereas my should be calculated as alpha y into w into Lx square, again Lx square. Okay, now we will see how to calculate the value of alpha x and alpha y. So for that, you have to refer table number 26 if you are going with a restrained slab, and you have to take the value of alpha x and alpha y are the moment coefficients. Say if when you come to simply supported, it is mentioned that alpha x and alpha y are moment coefficients given in 27. So again, there is a difference based on the support condition. If it is simply supported, you have to refer table 27. If it is restrained against rotation, or it is a restrained slab, you have to refer table 26 for getting the value of alpha x and alpha y. Right now, since we are dealing with simply supported slab, we will see how to obtain alpha x and alpha y from this table. Okay, so if you refer this table, you have Ly by Lx ratio given here, that is alpha x and alpha y. So both things, Ly by Lx ratio given here, that is this row. Ly by Lx is 1, 1.1, 1.2, 1.3, 1.4 and up to 3 they have given here. And we have the value of alpha x and alpha y. Okay, so based on the ratio of Ly by Lx, we have to select these coefficients from this table and substitute it here, and you have to calculate the value of mx and my. And then use this mx and my for the calculation of AST and the other things. Other steps remain same as that of one-way slab, but the major difference is the calculation of mx and my. That should be calculated based on the value of alpha x and alpha y, which should be selected from table number 26 or 27 based on the support condition. So this is the equation for calculation of moment. So what, let's see what after calculation of moment, what we should do. So we have right now calculated the value of mx and my, and again please note Lx, Ly should be the effective span in the respective direction. Lx should be along the x direction and Ly should be along the y direction. Okay. Now we will take up an example and see how to adopt this procedure. So for this, I have mentioned this example. Design a simply supported RCC slab, 5.5 meter by 4 meter, simply supported on all sides. So in the question itself, it is directly given that it is simply supported. So it carries a live load of 5 kilonewton per meter square, and we can use M20 grade concrete and Fe415 grade steel. And again, please understand that what is the minimum grade of concrete that we should use for structural purpose? Any idea for anyone? So earlier we used to use M15 and other grades, but now code restrict us to use a minimum of M20 grade concrete for structural purpose. So please keep this in mind. We have to at least use M20 grade concrete. We cannot go with a grade which is below M20. Okay. So now based on this data, so the data given in the question are, let's assume that effective span Lx is equal to 4 meters. So what is the dimension given? They are just directly taking 4 meter as the value for Lx. So if you want, you can just work out the value of effective span based on the condition given in the code, but that will not make much difference in the final answer. That is the reason if you refer some textbooks also, different textbooks will be following different manner. As you can see in this example, they have just directly taken effective span as the dimension given in the question, 4 meter. Okay, so that is up to you anyway. And we are provided with M20 grade concrete, Fe415 grade steel, and the live load is also mentioned in the question as 5 kilonewton per meter square. So these are the data given in the question. And one more thing we should note when we deal with the two-way slab is, see, I will take the corresponding clause. So as per clause 24.1 of IS 456 2000. So we will go to that 24.1. Okay, so here we have the main clause number 24, that is regarding solid slabs. And in this general, let's see what all things are given here. The provision of 23.2 for beams applied to slabs also. That means 23.2 is the condition for control of deflection. 23.2 control of deflection. That is, we have some span, effective span to depth ratio and other things mentioned here. That is again applicable in the case of slabs also. But we have some notes given here. Let's see what is given there. See, we have some notes here. Okay. So for slabs spanning in two directions, that is the case right now we are dealing with. The shorter of the two span should be used for calculating the span to effective depth ratio. What do you understand from that? Say in our case, we will be having a Lx and Ly. Ly will be always the larger dimension. But in this case, in the clause number 24.1, we are actually talking about the control of deflection. So for that, we will be having a span to depth ratio. So what code suggests is that for slabs spanning in two directions, the shorter of the two span should be used for calculating the span to depth ratio. That means when you consider this span to depth ratio, you have to always stick on to the value of Lx, not Ly. Ly edukkarada, you should always stick on to the value of Lx. The second note given is for two-way slabs of shorter span, that is up to 3.5 meter. For shorter spans only up to 3.5 meter with mild steel reinforcement, MS steel, that is 250. The span to overall depth ratio given below may generally be assumed to satisfy vertical deflection limits for loading up to 3 kilonewton per meter square. So different conditions are there. The length should be maximum length should be 3.5 meter and the load should be 3 kilonewton per meter square. Then in that case, instead of the things given here, we can use the span to depth ratio of 35 and 40 for simply supported slabs and continuous slabs. That is what is given in note 2. And one more thing is mentioned there, that is if instead of this MS steel, that is Fe 250, we are using high strength deformed bars of grade Fe 415 or greater is implied there, or greater, the value given above should be multiplied by 0.8. So it should be reduced actually. That is what code is suggesting. Clear? Is there any confusion in these notes? This is regarding the control of deflection. So basically we have some span to depth ratio which should be considered, which we used to consider for beams. That is again applicable in the case of slabs. And again specifically in the case of two-way slabs, we have to consider the shorter span for the consideration of span to depth ratio. Also for shorter spans, that is for up to 3.5 meter, and if the load is restricted to 3 kilonewton per meter square, we can take a span to depth ratio of 35 for simply supported slabs and 40 for continuous slabs if we are providing mild steel. And if we are using Fe 415, we have to actually multiply this 35 and 40 with respect to a factor of 0.8. That is what is given here. Is the things clear? Now we will go back to our question. Okay, so these were the things. So let me ask you, can we use this condition now? We have a suppose simply support. We are right now dealing with simply supported slabs. So can I take the span to depth ratio 35 in our problem? Our problem is this. Can I take it?
35 into 0.8.
Yeah, can I take 35 into 0.8?
Yes, because Fe 415 grade is used.
Okay. My first question is whether I can take 35 or not. After that only 0.8 will come into picture. So it is clearly mentioned that in note number 2, for shorter slabs having a maximum length of
3.5 meter.
3.5 is what is the shorter span of our slab?
4 meter.
So can we take that 35?
No.
So you cannot take that 35. Okay, that is the thing. So please keep that in mind. Now I am just going to confuse you. I thought of editing this, then I thought I will leave it to you anyway. Don't feel confused. Here I have taken this problem from one of the textbook. What they have done is that they have just assumed the overall depth to span ratio as 30. This cannot be related to the values given in the corresponding clause. But they have mentioned that it is regarding that, but that is not correct. We cannot take or we cannot talk with respect to the span to depth ratio of 35 because the length of the span here is 4 meters. That is restricted up to only 3.5 meters. So we cannot stick on to that value of 35 into 0.8 or something like that. But here what they are doing is that they are just assuming that the span to depth ratio is equal to 30 into 0.8. This feels confusing, but don't get confused. I have already told you that at this particular stage we can make any sort of assumptions. That is not at all a problem. You need not mention any span to depth ratio or something like that. You can even directly assume that the overall depth is equal to say something like 175 or 150 or 200 or something like that. That doesn't make any problem. Okay. So the statement they have made is actually confusing. They have just assumed the overall depth to be 30 into 0.8. So please don't relate these two things. That is the notes given, the things given in the note, and this multiplication with respect to 0.8. They are just making some assumption. That's all. Or for the sake of easiness, what you can do is that you just directly assume that the overall depth is 175 millimeters. You just neglect these two statements. Okay, and just assume that the overall depth is 175. In a later stage, we will just prove that this assumption will satisfy the control of deflection criteria, and we have already done that in the case of one-way slab, so it will be familiar for you, right? Anyway, we will be again doing it here. So I am just arbitrarily assuming that my overall depth is 175. And one more thing you have to understand is that for one-way slab, I have told you that we will be going up to, in the normal case, we will be going up to a maximum depth of 15 centimeters or 150 millimeters. But in the case of two-way slab, that can reach up to 20 centimeters. Okay. So here, normally, since we have bending in both the direction, a little bit more thickness will be required for the slab. That is the reason. Anyway, here we are making an assumption of overall depth is equal to 175 millimeters, and we are assuming a cover of 15 millimeters. Then again, we are assuming the diameter of main bar to be 10 millimeter. So as we have done in the previous cases, now I am just calculating the effective depth, which is equal to my overall depth minus my clear cover minus half of the diameter of my bar, main bar. Okay, so that will give me 155 as my effective depth. So right now I have the effective depth with me. Now I am just calculating the moments. So for that I require the factored load. So I am just going to calculate the loads. So calculation of design bending moment and shear force. We have the dead load. That is, we have the slab. We have the overall depth, which is assumed to be 0.175 into 1 into 25. This will constitute around, this will come around 4.375 kilonewton per meter square. Then we are assuming that we have some finishes having a thickness of 25 millimeter thick and plastering of 6 millimeter thick. You can either go like this, or you can directly assume like the total load corresponding to finishes is equal to 1 kilonewton per meter square. That is enough. I don't know why they have just put statements for confusing you. And if in the question, if it is given like you have a finishes of thickness 25 millimeter and you have a plastering of 6 millimeter thick, then you have to calculate the weight corresponding to that. If in the question it is nothing given like that, you can just directly assume that the total weight of finishes as say something like 1 kilonewton per meter square. Okay, I hope it is clear. So in this case, they have just assumed 25 millimeter thick finish and 6 millimeter thick plastering. So let's see how to calculate the value corresponding to this. So basically our thickness is this one. We are taking 1 meter width and we are assuming the unit weight of finishes to be 24. Similarly of plastering to be 24. This is slightly higher value. Anyway, they are just assuming the value of 24 here and obtaining the respective values. That is the weight corresponding to finishes and that of plastering as 0.6 and 0.144 kilonewton per meter square. Now they will calculate the total dead load as the sum of all these three quantities, and it is obtained as 4.375 plus 0.6 plus 0.144, which is coming around 5.119 kilonewton per meter square. Okay, this is the total dead load. And in the question, it is mentioned that we have a live load of 5 kilonewton per meter square. Therefore, the total factored load or the total design load will be 1.5 into this live load plus this dead load. That will come around 15.18 kilonewton per meter square. Is there any doubt in any of the portion which we have discussed till now? So we have seen Annex D, and we have two classification there: restrained slabs and simply supported slabs. And we have seen how to calculate the value of mx, my, and how to take the value of alpha x and alpha y. And we have discussed about two tables. Then we have taken up this problem, and here we have just assumed a overall depth, and we are now calculating the dead load and the live load, and finally we are finding out the factored load. Now we are just calculating the bending moments. So first thing is we have to calculate the value of Ly by Lx, and based on this value only from the table 27 we can get the value of alpha x and alpha y. So in this case Ly by Lx is obtained as 1.375. Therefore, referring to table number 27 of IS 46 2000, we will get the value of alpha x and alpha y as 0.0975 and 0.052. Let's fastly look that. Let's see. So to come down. So our value was 1. You remember the value? Just 1.375. Okay. 1.375. That is in between 1.3 and 1.4. So you have to interpolate and get the value of alpha x, which is coming in between these two values, and alpha y, which is coming in between these two values. So you just get the value of alpha x and alpha y. Then what do you have to do? Once you get the value of alpha x and alpha y, you just substitute the value of alpha x and alpha y in this, and substitute the value of acted load, which we have right now calculated. Then you substitute the value of Lx here. Lx is 4 meter in this case, so take the Lx square here, and you can calculate the value of mx and my. So this is how you will calculate the value of moment acting in the two-way slab. This is the major difference between one-way slab and two-way slab, the calculation of the bending moments. So once you find out the value of mx and my, the design remaining steps is same as that of one-way slab. So in that case, what we used to do was, first of all, we will check for the minimum depth based on the balance section equation, right? So for that we need the neutral axis, limiting neutral axis depth. Since we are using Fe415, we will have that value as 0.4, right? Substitute the value and find the value of D based on this equation, as we were doing in the case of one-way slab. And here you can see that D is coming around 92.66. This is the minimum depth required, but we have already provided a value of 155 millimeters. If you remember in the previous part, here you can see that we have assumed a overall depth of 175 and assumed a cover and diameter of the bar. After that, we obtained a effective depth of 155 millimeters. So our design is safe in view of this section. Okay. So now it is safe. Also, the section will be under reinforced section. So how can we calculate the AST now? So for that, similarly as we were doing in one-way slab, we will be using the equation corresponding to under reinforced section, that is this equation, and from this you can calculate the value of AST. And here, when you perform the design in the x direction, you have to substitute mx value. That is, you have calculated two quantities, one mx and one my. So first thing is that you have to perform the design along the shorter direction. That is, in that case you have to substitute the value of mx as the moment in this equation. So please take care of these things. These are some of the changes that we have in two-way slab. So when you use this equation to design the slab along the x direction, you have to substitute mu as mx and find the value of AST. So once you get the value of AST, we have already assumed the diameter of the bar. Then based on that, as we were doing, we have to calculate the spacing and round this spacing to a smaller value. In this case, we are obtaining a spacing of 174.25. So they are rounding it to 170 millimeters center to center, and you write your final statement. Provide 10 millimeter diameter bars at 170 millimeter C by C. Again, this clause 26.3.3 was regarding the spacing, maximum spacing of the bars, and we have some conditions regarding maximum spacing for primary reinforcement. Please remember, we have primary reinforcement and we were having secondary reinforcement in the case of one-way slab. But in this case, we will be having main reinforcement in both the directions. So there is no question of secondary reinforcement. Okay. So here we are providing 10 millimeter diameter bars at 170 millimeter center to center. Now the provided steel area can be again calculated. These things we have already done. So I don't think more explanation is needed here. Then you have to calculate the percentage of steel area also, which is, in this case, it is coming around 0.298. Why we were calculating the percentage of steel area and other things? Because if you remember back, initially we have made an assumption regarding the overall depth, and we have to ensure that that is safe in control of deflection. So for that, we are calculating the PT for calculation of FS. So I hope you remember these things. Right here. So basically, this is the thing. So provide steel area this much, and PT will be this much. So based on this condition given in your IS 456, based on figure 4, you can calculate the modification factor. So for that, what you require is the value of FS. For that, you require the area of cross section of steel required as well as that provided. We have already done that, and we also require to calculate FS. So substitute these values and find the value of Fs. So once you get Fs and the percentage of tension reinforcement, that is this one 0.298, you can find out the modification factor from this figure. So once you get the modification factor, what you have to do is that based on the clause given in your code for the control of deflection for simply supported beams, or that which is again applicable in the case of slabs, L/D ratio must be equal to 20. So please note here, even though they have confused you in the initial stage by mentioning that they have taken the L/D ratio as 30 and they again multiplied that by 0.8, when they reach this part, they are actually referring the clause corresponding to span having, means corresponding to slabs having span more than 3.5 meter. Okay, so please understand this, and based on L/D ratio is equal to 20, we are using this modification factor. Therefore L/D ratio will be equal to 1.60 into 20, which is coming around 32. Therefore from this the minimum depth required is 125. So again we have provided a depth of 155. So again our case is safe in point of control of deflection also. I hope things are clear to you. The design of beam along x-axis, but our design is not complete because we have two-way slab, so we have to design the reinforcement along the y-axis also. So after this, what they have actually done is, so after finding out the steel provided in the x direction, what they have done is, they are going to calculate the steel in the y direction. Okay, in the y direction. There is slight change here, so please do focus here. So when you calculate the effective depth, what will happen is that, actually I am not having the digital pen now, so I will try to draw using my mouse. So what will happen is that, so please cooperate, I am drawing with my mouse, so it won't be perfect. So basically we have already designed some reinforcement which is spanning in this direction, that is this will be your x direction. So we have already designed, that is 10 millimeter bars at 300 millimeter center to center spacing. That means if you take the plan, it will be something like this. We have some reinforcement going like this at a spacing of 170 mm C by C. Okay, now if you look from this side, what will be? It will be something like this. It will look something like this. I am just looking from this side. Okay, please do remember that. So before starting the design of finding out the reinforcement along the y direction, we already have some reinforcements like this, which are reinforcement which we have already provided in the x direction. So we are, please note, we are looking from this side, and when you designed reinforcement in x direction, you were actually speaking from this side. So you provided the reinforcement like this, because here the bending will be like this and here the bending will be like this. So since to prevent this bending, we have to provide reinforcements like this, and when you look the same reinforcement from this side, you will be seeing it as some dots. So this is where we have to start the design for finding out the reinforcement in the y direction. So here when you calculate the effective depth, what will happen is that this is your overall depth, which was 155. Then you have a cover here. Then you have this main reinforcement which is provided in the x direction. Okay, please note, this is the main reinforcement provided in the x direction. On top of this only you will be having the reinforcement which is effective in taking up the moment acting in the y direction. Okay, on top of the main reinforcement provided along the x-axis, we will have a set of reinforcement which will be responsible for taking up the moment acting along the y direction. Because if you look from this side, you have the bending like this, so you have to provide reinforcement like this. But this reinforcement will actually be coming over the main reinforcement which we have already provided in the x direction. So in this case, what will happen is that the effective diameter will be the distance from the top fiber to the center of your main reinforcement, which is provided on top of your main reinforcement provided in the x direction. Okay, so we have two sets of main reinforcement because we are having two-way slab. So when you calculate the effective depth, it will be overall depth minus clear cover minus diameter of bar in the x direction minus the diameter of bar which is assumed to be provided in the y direction by 2. Okay, I hope this thing is clear to you. This is one of the major difference when you perform the design of two-way slab. I hope there is no confusion in this. So you will be obtaining it as 145 millimeters. Is that concept clear? Is the calculation of effective depth clear to you? Can I get some response? Is it?
Yes, sir.
It's clear, right? Okay, so please take care of this. So once you calculate the effective depth in the y direction, again the procedure remains same. So what we will do is that, say since we have already calculated the minimum depth based on the balance section condition. So here you can see that the minimum depth requirement was only 92.66, but in the second direction also we are getting a dimension of 145 millimeters. So it is obviously safe as far as the over reinforced condition is considered. So that case is already satisfied there, and we can understand that since we have a effective depth smaller than the depth requirement of a balance section, we already have a under reinforced section in the y direction also. So you can use the same relation for calculating AST. So use the same relation, and here what we have to substitute is the value of my. That is a major difference. Okay, when you design the reinforcement in the y direction, in this equation you have to substitute the value of, for mu you have to substitute the value of my. On the previous case, when you design steel reinforcement in the x direction, in the same equation, instead of mu you have substituted mx, but here you have to substitute my. That is the only difference. Okay, so after substituting my here, you can calculate the value of AST, and in this case it is coming around 250.21 millimeter square. So you again assume the same diameter bar or whatever things you need, then find the spacing requirement and round it off. Here they are getting it as 313.74, and again we cannot provide that much spacing because the clause in the code restrict to a maximum spacing of 300 millimeters, and we have some more conditions, 5 times D and other things. So based on that, you provide the spacing. Okay, so in this case, they have provided 10 millimeter diameter bars at 300 millimeter center to center. Then we are just calculating the amount provided, means actually provided reinforcement, that is coming around 261.67 here. Okay, so again after that only they have just proved that the assumption of depth was correct. Okay, because they have just after this they have just calculated the value of Fs and refer figure 4 and found out the modification factor, and then they proved that the assumed value of 155 was safe, which was already satisfying the control conditions for control of deflection. So once you complete up to this, your design for flexure for this slab, two-way slab is over. We have designed in the x direction as well as in the y direction. Now the thing remaining is we have to check for shear also. Okay, we have to check for shear also. So for this, the procedure remains same as that of your one-way slab. You calculate the value of tau v, find the value of Vt, tau c, as well as tau c max. Then you have to calculate the value of k. The same thing. And normally, in normal case, you will be getting tau v as less than tau c by 2. So you need not be in need of providing any shear reinforcement in the case of slabs. So this is it. So after this, you have to provide the detailed drawing also. That will complete your design.